Welcome, explorers of science. Today, we're embarking on an epic journey into the invisible yet incredibly powerful world of thermophysics. Think of this explainer as your ultimate survival guide for acing your grade 7 exam on insulation and energy saving. We're going to travel from the freezing winds of Antarctica all the way to the brilliant white islands of Greece, and even launch into outer space, all to master the fundamental forces of heat. I am absolutely thrilled to be your guide today. So let's dive right in.
Unit 1. Heat Loss and Gain.
Our journey begins in our very first biome, where we'll track the elusive movements of heat as it escapes and enters our environments. Let's start with question 1. In what 3 ways can heat energy be transferred? Well, like the elemental forces of nature, heat travels through conduction, convection, and radiation. Whether it's traveling through a solid metal spoon, swirling through the air, or beaming across the vacuum of space from the sun, heat is always on the move using one of these 3 fundamental pathways.
Which brings us to question 2. Why do we actually want heat transfer to happen? Well, simply put, so we can make things warmer. I mean, imagine a freezing winter night. You switch on a heater in your room. You actively want that heat to transfer into your habitat, right? Notice how the heater brilliantly uses convection to circulate warm air and radiation to beam warmth directly to you, turning a cold room into a cozy sanctuary.
Now let's leave our cozy room and travel to one of the most extreme environments on Earth for question 3. How do penguins prevent heat loss in the freezing winds of Antarctica? It is truly a marvel of nature. To survive, these incredible birds huddle tightly together in a massive group, sharing their collective warmth. Furthermore, their specialized feathers are literally designed to trap a layer of air right against their bodies. This trapped air acts as a shield, drastically reducing heat loss through convection.
Back in our domestic habitats, humans have engineered our own survival tools. Question 4 asks for an everyday device designed to prevent heat loss. Well, look no further than the humble electric water geyser. Think of it like a thermal vault. It's heavily insulated to trap the heat inside, preventing energy from escaping into the surrounding environment. This ensures that when you turn on the tap, the water is wonderfully hot.
And this brilliantly illustrates our next core concept. Let's move to question 5 and see how this builds into the difference between heat loss and heat gain. It's basically a continuous tug of war. Heat loss is when your energy escapes into the wild environment around you through conduction, convection, or radiation. Heat gain, on the other hand, is the exact opposite. It's when you absorb or pull heat energy from your environment.
Let's paint a clearer picture by tackling questions 6 and 7 back to back. 3 examples of heat loss and 3 of heat gain. On the loss side, picture your own body constantly radiating heat into a cold room. Or imagine a campfire where heat escapes into the night sky through convection and radiation. Or even a steaming mug of hot tea losing its warmth through the ceramic cup via conduction. Now contrast that with heat gain. Imagine basking on a beach, your body soaking up solar radiation, or opening a window on a blazing summer day and feeling a wave of hot air warm your house through convection, or simply a pot of food sizzling as it gains heat directly from a hot stove through conduction.
Humans have really learned to master both sides of this equation. For question 8, we ask, how does a solar water heater absorb heat and prevent heat loss? Well, it's a 2-part stroke of engineering genius. First, it uses deep black pipes to fiercely absorb radiation from the sun, heating the cold water inside. Then, it stores that newly heated water in a heavily insulated tank. So it hunts for heat and then hoards it like a thermal treasure.
Unit 2. Using insulating materials. This brings us to the magical, protective materials that defy extreme temperatures, the insulators. Let's look at questions 9 and 10. First, what do insulating materials actually do? Well, they act as heroic shields. They don't stop heat entirely, no, but they severely delay heat loss and heat gain. And why does this matter? That's question 10, energy conservation. By using insulators, we conserve energy. We save immense amounts of power and resources by preventing the unnecessary heating or cooling of our buildings. Now, let's zoom out to a planetary scale for question 11. What is the Earth's natural insulation layer that keeps it warm? It is our magnificent atmosphere. Wrapping around our planet like a giant, life-saving greenhouse, it traps just enough solar heat to keep our oceans flowing and our ecosystems thriving.
Down on the ground, how do we mimic this? We're going to tackle questions 12, 13, and 14 all at once here. What are the best insulators and why? The secret superpower is trapped air spaces. Because air is a terribly weak conductor of heat, Materials full of tiny air pockets are incredible insulators. And why small spaces? Because it restricts the air from moving freely, which basically kills heat transfer by convection. Just look at nature and human invention. We've got wool, feathers, cork, straw, fiberglass, and styrofoam. Every single one of them relies on the magic of trapped, motionless air.
So the crucial point is how we use this daily. Question 15 asks for 2 everyday objects using insulation. Well, think about your home's ceilings. They're the frontline defenders, keeping the roaring summer heat out and trapping your cozy winter warmth inside. And think about woolen clothes. When you wear a thick wool sweater, you are literally wrapping yourself in tiny trapped air pockets that prevent your own body heat from escaping into the cold air.
But what if you leave the Earth's atmosphere entirely? For question 16, we ask, how do NASA spacecraft protect astronauts from the deadly extremes of space? With absolute cinematic grandeur, NASA engineers use multiple layers of specialized materials. They use highly reflective outer layers to literally bounce away the blazing radiation of the sun, and thick inner insulating layers to trap the astronauts' precious body heat from escaping into the freezing void of space.
Unit 3, Conserving Heat in Homes and Buildings.
All right, let's bring our spacecraft safely back down to Earth. We're now focusing on the thermal battles fought inside our very own homes. Question 17 asks a simple but absolutely important question. Why do homes get cold in winter? Simply because of relentless heat loss. Heat is constantly trying to escape through your walls, doors, windows, and roof, right out into the freezing environment. And why does it do this? That's question 18, the strict direction of heat flow. You definitely want to remember this universal law for your exam. Heat energy always moves from where it's hot to where it's cool. It always seeks to balance out.
So if heat is always trying to invade a cool space, how do we fight back in summer? Question 19 asks, why do people in very hot countries like Greece paint their houses white? If you've ever seen those dazzling, beautiful white Mediterranean walls, you know it's not just for aesthetics. White surfaces brilliantly deflect and refuse to absorb solar radiation, ensuring the inside of the house remains a cool oasis during a blazing hot day.
Now, let's lock in this knowledge with an interactive matching challenge for question 20. Every element of a house has a specific defensive function. Ceiling insulation stops hot, buoyant air from rising and escaping into the roof. Wall insulation blocks the transfer of heat directly through your brickwork. Heavy curtains act as a shield, stopping heat from bleeding out through thin glass windows. And plush carpets provide a lovely layer of trapped air that drastically reduces heat loss into the cold ground beneath your floors.
Unit 4, Traditional Indigenous Homes.
For our final biome, we don't need modern fiberglass or space-age NASA tech. We are going to marvel at the brilliant, ancient architectural wisdom found right here in South Africa. Let's tackle our final questions, 21 and 22. Zulu and Ndebele huts are absolute masterclasses in thermal physics. Long before modern textbooks even existed, these builders utilized 3 incredible characteristics for temperature control. First, having small or no windows drastically prevents heat loss in winter. Second, their thick thatch and reed roofs naturally trap massive amounts of air, providing supreme insulation year-round. And finally, their wide, overhanging roofs are perfectly designed to cast cooling shadows over the walls during the brutal summer sun. It really makes you wonder, doesn't it? As we face global energy crisis today, what other brilliant climate solutions are hiding in the ancient architectural wisdom of the past? Keep exploring, and good luck conquering your exam.